Hi there guys, we're going to do some multiplication of matrices here. This is 9B from the HLAA book, and this starts off with some nice questions in context. You've got this one about frappes, cappuccinos, iced coffees, and the days of the week associated with each of those items, and the numbers which are sold on each of those days of the week essentially. That's pretty nice, and as a matrix, and then they add in prices then, and so ultimately you're going to need to find out the total amount of money that's made in each week or per day or whatever. Okay, and we're going to do that through matrices. So there's nice questions in context here, but just before we do that, I've just skipped ahead a little bit, and I'm going to go through the process of multiplying matrices from this definition essentially. Okay, so let's actually look at the mechanics of this one first of all. So let's take one. Let's do here 5, 6, and 1, 4, and let's times that by, I don't know, let's times it by 5, 0, and 3, 1. Okay, now the way in which you do this is you times the first row, the elements in the first row, by the elements in the first column of the second matrix. So elements of the first row in the first matrix times by the elements of the first column in the second matrix, and then we're going to sum those answers together, sum those products. Okay, so in this case we're going to do 5 times 5, so we've got 25, and then we're going to do the 6 times by the 3, so then we've got plus 18 there, and then we're going to do the first row times by the second column, and that's going to go in this position here. And obviously we're going to sum those elements as well. So 5 times by 0 is 0. That's pretty convenient. And then 6 times by the 1 is going to give us 6. So we're going to do plus 6 there. And then the next two answers come from the second row times the first column, and then the second row times the second column. Okay, so 1 times by 5, and then 4 times by 3, so give us 12. And then we can do the same again with this times by this. So we've got 1 times by 0, again is 0. And then 4 times by 1 is 4. Okay, and it's pretty straightforward then to put all of that together. So we've got 43 there, 17 there, and 6 there, 4 there. Now, when you're looking at this matrix at the end, so this one here, you can compare it to this one here. You might notice something. In fact, you might notice that the 6 and the 4 are the same in both of those cases. Now, that's down to the fact that we've got zeros and ones in this part of the second matrix which we're using there. Now, just to add in a bit extra there, in fact, if we'd have done this instead, if we'd have said 1, 0, and then 0, 1, this is what we call our identity matrix. This is the identity matrix which is of order 2, so it's a 2 by 2 matrix there. So this is your second identity matrix. And the identity matrix is like having a times by 1 in a situation of normal multiplication. So basically, when you times by your identity matrix, you get back the same answer. So let's just check that one out. So what would happen here, if I did 5 and the 6 times by 1 and 0, well, that would give me 5 there and 0 there. And then this would stay the same. So we're getting 5 times 6 times 0, and 5 times the 0 and 6 times the 1, and sum them together. That's the same. And likewise, the 1 and 4 against the 0 and 1 we've already done. That's there. And of course, the 1 and 4 against this here, we're going to get 1 times 1 is going to give us the 1, and the 4 times 0 is going to give the 0. So we're going to get back to that original matrix, which is 5, 6, 1, 4 there. So this is our identity matrix. And in fact, we could actually have put that one at the front and it would have worked the same. Now, I'll let you verify that. but it's good to know that not only have we got the 0 matrix, you know, essentially like with numbers, we've got 0 there. We've also got our 1, if you like, which is our identity matrix. Okay, now things to note about our multiplication, that you definitely need the same number of columns in the first matrix as your number of rows in the second matrix. So if we call this a matrix which has m rows and it's got n columns, and this one a matrix which has got p rows and q columns, then we've got an m times n matrix in the first one, and we've got a p times q matrix in the second one. Those are the dimensions of our two matrices there. Now, the n and the p have to be the same. So we need two elements there to times against two elements there. The n and the p have to be the same. Now, n and p are the same, but also it's worth noting that you end up with a matrix which is m times q. That's what you're going to end up with. So you'll end up with the m rows in the answer here. So we've still got m rows there, and then we end up with q columns there. So that's what happens, and the n and the p sort of disappear, if you like. Okay, let's just show another example of this one. Okay, so for example, I'm not going to do all the mechanics of the numbers here, but let's just say, for example, we did a 2 by 3 matrix. We did 2 by 3, you know, so 2 rows and 3 columns, and then if we timed that by, let's say, a 3 by 2 matrix, so we'd have this matrix here. So this would be 3 by 2. This would be 2 by, sorry, I'm making a mistake there. This would be 2 by 3, and this one would be 3 by 2. Then you're going to end up with here a 2 by 2 matrix, because the 3's are essentially going to disappear. The 3's have to be the same. So, you know, we're going to end up getting this and this and this times by this, this and this. That's going to give you this answer here. And then we'll end up getting, let's change color. Let's put this purple on. So then we do this, this, this times by this, this, this. That's going to give us this answer here. And then we'll do this, this, this times by this, this, this. It's this answer here when we sum all of those together. And then finally, change color again. Use this pink one. This times this, this is our final answer here. And you can see that we're left with that 2 by 2 matrix in the end. Okay, so, right, well, once you've understood all of that, you don't really need this, to be honest. This is the definition of how to multiply things together. So let's just go through the definition briefly. It says if P equals AB, so that's what we're doing. We're calling this the vector A, we're calling this the vector B here. So P is our answer in this case. Then each element of P named Pij. So let's think about this. Say, for example, this one here would be this one here. So we say that P ij, so it's found by summing the products of the elements of row I in A. Let's just think about what this is. This is P2, 1. That's second row, first column. Rows and then columns when we're in matrices. So this blue one comes from summing together the products of each of the elements in row I. So row I would be the second row from the first matrix, from A. So that's what we did. And then with the elements of column J of B. So we want second row of A and first row, so first column rather of B. So that's first column of B there. So that's what we're timesing together, and that's what we're summing. So this is really kind of difficult to unpack, but to be honest, if you know how to do matrix multiplication, you don't really need to unpack that too much, okay? Right, so there you go, there's that. So I'm going back to the original example now, and The original example, if you remember, just had the frappes, the cappuccinos, and the iced coffees, the number of each of those things sold on each of the days of the week. So this matrix is holding a lot of information about frequencies here. Now, they call this the matrix F at the top, and then they call it W down the side. I think that's a mistake. Underneath, they're talking about the prices of these things. The frappe is €4, the cappuccino is €3.50, the iced coffee is €2.50. Okay, and then they're coming up with a revenue matrix, which turns out to be a vector, in fact. And so they're saying, look, the 28 frappes which are sold on, let's just put this together, okay, do this thing here. So they're saying the 28 frappes which are sold on Monday, I think that was at the start, plus the 32 cappuccinos, plus the 16 iced coffees, if we times them each by their prices and add them together, we're going to get the total revenue for Sunday or Monday. My apologies. I'm just going to check back on this one. What were the days for Sunday? Sorry, for Sunday. Okay, so this is giving us Sunday here, all of these ones put together here. Now, this actually comes from a multiplication of matrices, and we'll see that in a second. But you can see that what they've done is they've taken a 3 by 7 matrix. No, they haven't. They've taken a 7 by 3 one. Okay, your 7 by 3 matrix, and they've times it by, well, look, we've got 3 there, so it's got to be 3 here, and in fact, we're only going to get our 3 prices there. So what we're doing is we're timesing a 7 rows by 3 columns matrix by, and then we're going to times that by a 3 rows and 1 column. Okay, so now you can see that kind of the 3 and the 3 is going to cancel, and you're going to end up with your 7 by 1 matrix, which is just 7 rows and 1 column, which is essentially just a vector as it's coming out there. Okay, so that's what we're doing. You should be able to see that's pretty straightforward. And that's going to give you your prices for your revenue on Sunday, Monday, and so on. Okay, let's just look at what they've done in the book for that one as well. So they've said, look, you can come up with a price matrix. There you go. Price matrix is 3 by 1. And then you've got W times by P, not F times by P as they originally said. Here we go. Let's just take this one here. And okay, so here we go for this one here. So they've kind of broken it down. They've kind of gone backwards. And they said, well, this is where the multiplication must have come from. Okay, so we've got these ones times these ones gives you this, these ones times this gives you this, and so on. And you obviously don't need to do 2 for this because there's not a second column in the second matrix. Okay, now I just thought of a little extension here actually. And if you wanted to actually have your total revenue here, so this is obviously just giving you a vector for each of your days. If you want your total revenue, you could actually do that by adding on another matrix at the start. And if we added on 1, 1, 1, 1, 1, 1, 1, so 7 ones, then you could do this first, okay, and then you could times it by this one here. And when you times this, which is this, okay, when you do this times by this, which is frankly just this, okay, we put this in front of this essentially, then we'll get 1 times this plus 1 times this plus 1 times this plus 1 times this, and we'll have a 1 by, what have we got? We've got a 1 by 7 times by a 7 by 3 times by a, for this last one, this one is going to be a 3 by 1. So the 3 and the 3 sort of cancels to give you a 7 by 1 matrix, 7 by 1. That's what we're left with there. And then when we times that by this one in front, the 7 and the 7 is going to cancel, leaving us with a 1 by 1 answer. That's just a way of getting one particular summed answer at the end there. And you can imagine that that's the kind of thing that a computer program might wish to do. Okay, so we might wish to get that answer out from, I don't know, say for example, from a till register at the end of the week. Okay, right. So let's look at a little bit more here. What else is it saying? Oh, that's what we went through, in fact. So there's just the mechanics of that. So we're going back there. Okay, so that's good. I think we've got another question coming up here. We've got this one, example 2, and then after example 2, we're going into investigation there. And there's properties of matrices, and then there's time based. There's only really one major example left, but there's also 2 investigations here as well. Okay. Now, this little bubble which they come up with here, which is if A has dimensions m times n and B has dimensions p times q, then it says that n is equal to p essentially. And when it does exist, if there is an answer to this, then your final matrix will be in the form of m times q. That's what we talked about already. Okay, so in example 2, it says a diet research project consists of adults and children of both sexes. The number of participants in the survey is given by this matrix here. So we've got adults and children in the first 2 columns. And we've got in the rows the males and the females in this research project. So for example, there are 75 adult males who are in this research project. Okay. You might be able to hear outside at the moment. School is finishing for people today. Right, so what I'm going to do is I'm going to take this part here. So this is still example 2. And I'm going to take this. There's a mistake in this question, by the way. Just we might as well see it now. In part B here, which probably, well, obviously hasn't been fixed in the book. In part B, it says explain the meaning of A, B, 3, 2. But then in part B in the answer here, you can see A, B, 2, 3. And quite clearly, in fact, 3, 2, row 3 and column 2 doesn't exist in the answer. So there's a mistake here, which we'll deal with when we get to it. Anyway, I'm going to take this here, okay, to talk around. And I'm just going to put on the information here again as well. So we had, this was adults, and this was children here, and this was males and females. This was males, and this is females. That was the information from the previous page. Okay, so what's it saying? It's saying that we also have this chart, this second matrix here. We've got B, and B is now splitting up the daily intake of protein, fat, and carbohydrate that adults and children would be taking in. So the number of daily grams of protein, fat, and carbohydrates consumed by each child and adult. So it's fixed. It's not changing per adult. It's fixed per adult. And perhaps this is an assumption, or perhaps this is a specific experiment here where they're being given out these quotas. Okay, so first of all, let's say determine AB. Well, AB is fairly straightforward. You're going to times 75 and 180 by the 15 and the 8 to come up with your answer here. Okay, and it's best to show you're working out as we go as well. Obviously, you can do these on your calculator as well, but as you start doing this, it's a good idea to do all of the techniques just in case in an exam question they say, well, look, what's this? Find A at some stage, you know, and then you've got an issue if you don't know how to do all of the techniques. So the mechanics of it. Obviously, if you get this in an exam situation just like this, you could actually type this into your calculator and do your product on your calculator. Okay, so yeah, 75 and 180 times by the 15 and the 8. So to make some sense of that, that's the male adults, so 75 male adults, times by the protein which the male adults are taking in, and then the 180 male children, so boys, times by how much protein the those 8 children are taking in gives you the total amount of protein consumed by all males. The 15 adults, sorry, not the 15 adults, the 75 adults taking in 15 grams of protein, and the 180 boys taking in the 8 grams of protein. So that's what it's giving you. There's a particular meaning for this. Okay, and obviously you can just continue with this. Again, let's just check. We're getting a 2 by 2 matrix there, by a 2 by 3 matrix there. 2's cancel. We end up with a 2 by 3 matrix. This is a 2 by 3 matrix. We're happy with this. Okay. Okay, so for the next bit, it really should say, what's the meaning of A, B, 2, 3? So not 3, 2. And so they're looking for this one here. So that's 2, 3. It's the second row and the third column. And so again, what's the meaning of that? Well, that's going to be 110 women and 250 girls, and their consumption, respectively, of carbohydrates. So the women, so female adults, are having 25 grams of carbohydrate each, and then 250 girls are having 20 grams of carbohydrate each. So if we sum those things, we're getting the total amount of carbohydrate for all of the females there. So for the girls and for the women. Okay, so finally it says explain why BA does not exist. Well, BA does not exist. Let's think about BA. BA is the matrix which is what's this one? This one is a 2 by 3 matrix. This is a 2 by 3 matrix. And A is the matrix which is 2 by 2. Well, it is not possible to do it this way around because you have a different number of columns in B to the number of rows in A. So that's not going to work. Those two things need to be the same. Let's just have a look at the answer that they give here as well. So it says BA is not possible since the number of columns in B is not equal to the number of rows in A. Okay, they said exactly what I've just said there. Okay, so there's an investigation which turns up afterwards here, which is obviously worth doing, but I am going to skip ahead to the results of that investigation, and I've actually just copied this one here. And there's some particular properties of matrix multiplication that you should be aware of. And that's that doing AB is not necessarily the same as BA. In fact, normally it won't be possible. In fact, that's what we just looked at in the previous example. We showed that BA didn't work, whereas AB did. Now, there are nominal cases where that will work. So, for example, if we use the identity matrix as A and the identity matrix as B, then it's obviously not going to matter which way around you swap those two things. So occasionally it might work, but most of the time it's not going to work to swap these two things around. But that's called the non-commutative law of multiplication. Now, we have all of these laws for multiplication normally. So for example, it is commutative. Multiplication is commutative if you can change the order of the product which you have. So 2 times 3 is the same as 3 times 2. That's called commutative. We just don't often use that, but that's the proper terminology. Now, associative means you can do things in a different, you can sort of bracket things up in a different way. So for example, if I did 2 times 3 times 4, I could either do the 2 times 3 first and then times 4, or I could do the 3 times 4 and then times 2. It wouldn't matter which way around I did that. So that's actually working with matrices here. So, you know, when we came up with a pretty long example before, I think I said that if you come up with, you know, a 1 by 7 matrix, and then a 7 by 3 matrix, and then a 3 by 1 matrix, I said, well, look, we can do these two first. You'll end up with a 7 by 1. and then you can do what's left over and cancel the 7. You'll end up with a 1 by 1. Now you can check that out the other way around. If you did these two first, 7s are going to cancel. You'll end up getting a 1 by 3 matrix. And then when you do these two together, then so these two together now, you'll get 3s cancel. You'll end up with a 1 by 1 matrix. You can see you're getting the same dimensions at least from that. Okay, and you can verify this yourself if you don't believe me. I suspect that most people won't bother doing that. Okay, but we've also got the distributive property of multiplication here. It's basically saying you can multiply out brackets with these things as well. Now you can see this thing here. If you add two matrices together and then times by your A, you get AB plus AC. And likewise, if you've got the A at the end there. I'm not going to go into much detail in that. You can see that they've just added a little note on for this as well about pre-multiplying and post-multiplying by A. I'm not going to go into a huge amount of technical detail on this. It should be fairly clear from your examples how to do the questions without really knowing too much about these, to be honest. Okay, so there you go. And we talked about the identity matrix here as well. And here again, we've got the identity matrix for order n that they're talking about in this case. You can see the way they set these things up. So, you know, the way in which they're setting this up with a ton of dots in between, just to say we've got n rows and sorry, n columns and we've got n rows here. And so this is your identity matrix of order n. Okay, and it doesn't matter if you do A times IN or if you do IN times A, so long as the multiplication is possible. Okay, in other words, here you've got n, we're already talking about n columns and n rows in this one. Yeah, that's right. And in this one, we've got n rows and we've got n columns here. Right? So long as you've got that, then these things should work. Okay. Right then, guys. Well, thanks for that. Nearly failed at the last hurdle there. So here we go. We've got 9B here. We've got 3 questions on page 381, and we've got some more questions in context there on the next page. Obviously, get maximum practice on this. Thanks for listening to the video. Sorry, it's long. Next time round, we're then talking about products of matrices. So we're talking about matrices to certain powers as well, by the looks of things. Okay, which is interesting, but that's for next time. Thanks for listening, guys, and good luck with the exercise.